The ability to land and take off planes from ships makes you reconsider the potential of human capabilities. Thanks to NATO's invitation, I experienced the United States ship George Bush firsthand, landing and taking off on board a C-2. In case anyone doesn't know, on aircraft carriers, to take off, the planes use a catapult that hooks the front wheel and in 3 seconds propels the plane to the necessary speed to fly. And to land, there are cables on the deck that allow the plane that is going to land to hook onto them and thus brake. Today we are going to talk about these two systems, and I am finally going to reveal to the public how many G-forces are endured in both cases. To reach an aircraft carrier at sea, you can go by plane, helicopter, or another ship. The plane is clearly the best, as it allows you to experience the sensation of landing with the cable and taking off with the catapult. And that's how I got to the aircraft carrier aboard a 102 Greyhound. A transport plane, the only one capable of landing on modern aircraft carriers. Anyone who gets on this aircraft must carry a survival kit. Okay, this is the vest that we have to put on. If we pull here, it inflates, in theory. And here we have, well, a whistle. Something they say lights up the water in case they need to see us. You should also wear a protective helmet that has attached some goggles and some noise-canceling headphones. At first, I thought the noise cancellation topic was for when we got to the aircraft carrier. Inside the 102, the noise level is around 95 decibels, making it impossible to converse with the person beside you. In fact, we were passing our mobiles, writing notes to be able to talk to the person next to us. This aircraft has backward-facing seats, possibly due to G-forces, according to online sources. We'll reflect on that later. The aircraft only has 2 windows, one on each side, and guess where I sat? You may notice what looks like smoke in the cabin. This is because the 102 lacks an interior temperature control system. Therefore, when it reaches a cruising altitude of 20,000 feet, the air inside the aircraft is very cold. Our journey lasted an hour and a half as we approached the Adriatic Sea, where some NATO exercises were being carried out and the aircraft carrier was participating in them. During all that time, the inside of the aircraft cooled down, and later, the hot air from outside descended. When getting into the aircraft and coming into contact with all the surfaces that were very cold, it condensed, so it's condensation, not smoke. Aircraft carriers used to have 4 cables, but the most modern ones now only have 3. This is because each cable actually represents thousands and thousands of hours of work and maintenance. Therefore, in the end, it was decided to remove one. The system that allows the plane to hook the cable is simply a tab that, due to the angle it forms, hooks the cable. To do this, they are lifted with steel wires on the deck. In this way, they are kept a few centimeters off the ground so that the plane can easily catch them. But these wires are designed so that a plane wouldn't even notice if it steps on them. But it's vital that the plane carries the correct angle so that the hook can catch the cable. We will talk about this angle of the plane in detail in the next video. The plane's hook is checked every 10 landings and is made up of 2 main parts, the hook itself and the tongue that grabs the cable. Both have different operation times. The tongue, for example, is changed much more frequently than the hook. Keep in mind that every time it lands, it hits the ground. It's interesting to see that on the deck, there are plates installed so that they are the ones that take the impact of the cables. That way, when they are already worn out, they would simply be replaced instead of wearing out the surface of the ship. The cable may appear simple, but the system is highly complex. This is because the aircraft must be gradually slowed down so that the deceleration is acceptable to the people who are landing. The system consists of 3 parts, the first being the stop cable. This is the cable that we all see that the planes hook onto. It has a thickness of approximately 3 centimeters in diameter and is made of steel. These cables must be changed every 125 landings, so the system must be changed very quickly. In less than 3 minutes, a cable can be completely changed. Then we have the purchase cables, which I don't know how to translate into Spanish. Well, they are very similar to the stop cables, and in fact, they hook onto them, but they are actually much longer and connect the cable to the stop motor. When an airplane lands on an aircraft carrier, what happens is that part of the purchase cables are unwound, and that's how the aircraft is stopped. Look at this video how the stop cable hook and the purchase cable is here, but when the plane hooks on, the purchase cable unwinds. And this part, which at first is next to the white nozzle, suddenly you can't even see it because it's so far away. Because the purchase cable has unwound a lot and the other end of the purchase cable leads to the stop engine, this is the part that breaks the plane. We have a piston filled with hydraulic fluid at both ends. It's connected to the purchase cable, so that when a plane hooks up and generates a force by stretching, the cable starts to unwind, and that implies a movement of the piston. The hydraulic fluid starts to move towards another piston, which has a pressure of 40 atmospheres, and therefore generates a tremendous force against the piston, thus stopping the movement of the aircraft. The reality is that the system is much more complex because there are 2 pistons instead of 1, and it's a bit more convoluted, full of moving cables, but the idea is the same. If there wasn't a stop engine and the cable was simply anchored at 2 ends, there wouldn't be a progressive deceleration. The plane would hook the cable and stop abruptly, causing a spike in forces. The landing was unbearable. I'll show you the video of my experience. Remember that in this plane you go backwards, therefore when braking, if in a car you go forward, here I would stick to the It's not very noticeable, but look at the hand here, how it shoots out upon impact. Well, how many G-forces do you think were endured? Well, here you have the video with the G-force record recorded with the mobile's accelerometer. The Z-axis represents the vertical, up-down force, while the Y-axis represents the longitudinal, forward-backward force. And the 10-axis is transverse, running left to right. Let's analyze this for a moment. The first thing that catches the eye is that the peak of G-forces is on the Z-axis, that is, downwards. This is because the plane is moving at a descending speed downwards, but the moment the plane's wheels touch the runway, its descent stops instantly, causing a peak in G-forces. In parallel, the braking force, the axis, is visible, which also increases at impact. When the plane touches the runway, it slows down due to friction. And then we see how that braking force progressively increases until it then starts to decrease and drops practically to 0. This is because, as we have mentioned, the cable generates a progressive deceleration and the plane is braking from the moment it touches the runway until it stops. So looking at this, we can see that the deceleration, the braking force, reaches up to a value of 1.5 Gs. I conducted an Instagram survey asking how many Gs people thought would be reached upon landing. Only 10% remained within the correct range. We'll reflect on the Gs at the end of the video. Look, I asked the pilots of the 102 how many Gs this plane can pull. Plane. How many Gs can you pull?
It depends which way we go for it. Maybe 2 to 3, but our landing sometimes can get up to 6 feet.
Are you saying that this plane doesn't pull more than your input doesn't seem to be a metric system unit? Please provide a valid metric system unit in a turn. Upon runway contact, an abrupt impact can cause a peak of up to 6G. Apparently my 3G landing was somewhat gentle. I asked him this because we made a very wild turn, but we will see that in the next video. To take off, only the American supercarriers and the French aircraft carrier use a catapult. Russia, India, and China use a system with a ramp where maximum power is applied before the plane moves and it takes off by the sheer thrust of the engine. But they are very limited by the weight they can take off with, as they take off much slower than with a catapult. But then, why don't they also use a catapult? Because the system is tremendously complex. Let's take a look. Currently, there are 2 types of catapults, steam and electromagnetic. Let's start with the steam ones, which are the most used. It consists of a protruding tooth on the top of the ship's deck, which is what will hook onto the Morrow train to propel the plane. This tooth is connected to 2 pistons below, which will generate the force. The pistons are connected to a tank full of pressurized steam. This steam comes directly from the nuclear reactor. But, just like I explained in the previous video, this steam has not had direct contact with the reaction itself, but the steam is generated by cooling a closed water circuit, which does come from the reaction. Therefore, that steam is not radioactive when the catapult is activated to launch a plane. That steam from the pressure tank is allowed to pass at full speed towards the pistons, which suddenly feel a tremendous force and move at full speed. As the pistons move, the tooth will also move, and that is what finally pushes the plane. And later, water is used to stop the pistons. At the end of the catapult, there is a hole filled with water, and the pistons have a protrusion at the front that embeds in that hole with water that stops them in just 3 meters. But there is still a very important part of the catapult, this one here. Probably almost no one knows what that hook does, as it is what keeps the plane still in its position and lets it go when the launch is activated. Look, when the tooth catches the wheel, it generates a forward force that, combined with the engines already at maximum power, the plane should be moving forward. But the only thing that keeps it still is that hook. When the catapult's full force is activated, the plane is released. In the past, a hook similar to this one was used, but it was designed to break under certain force, so that the sum of the force of the engines plus the catapult would literally break it, and in that way, the plane would be released. The reality is that the system worked well, but this hook had to be changed for each launch, and it was not very practical, so the current system was invented. The idea is basically the same, but the plane is not released as a result of a break, but it works by the law, which is the one that governs elastic deformations. What I'm going to tell now happens in milliseconds and everything begins. Once, the plane already has its engines at maximum power and the catapult is suddenly activated. Inside the colorful part of the bar, there are a series of rings. One of them, this yellow one, is fixed. When the catapult is activated, part of the bar stretches a few millimeters by its own elasticity, enough to leave a part free to move and start the sequence for the launch, which ends with a small slide until some tabs are released that were holding the aircraft. There are different bars for different aircraft, as depending on the weight of the aircraft, it will need more or less thrust to take off, and different types of bars are needed, since it is that forward force that starts the launch sequence. In case something fails and the sequence does not activate, is the material made to break and release the aircraft if something has failed? But in reality, this happens very few times or practically never. Today it is said that these catapults will be the future. They work with a linear induction motor, exactly the same idea that we discussed in the video about Hyperloop. A linear induction motor is composed of coils on both sides of a rail, which when generating an electric current in the coils creates a magnetic field. That magnetic field generates an electric field in the rail, and that electric field in the rail generates a magnetic field that interacts with the first magnetic field and generates movement. Electromagnetism is truly complicated to understand, but for you to understand, it's as if it suddenly repelled the rail and the moving part, and that's why it suddenly comes out at a certain speed. This type of catapults have clear advantages over steam ones, and that is, they don't take up as much space, since there's no need for a huge infrastructure under the deck to store the pistons or the pressurized steam. In addition, the system can be put into operation in a matter of minutes, while steam catapults need hours and can be operated with far fewer people, which will obviously reduce costs. But the downside is that they have not yet proven to be as reliable as steam ones, so we'll have to see how the issue progresses. Many have asked about aircraft carrier takeoffs. Do you use the afterburner to take off?
It all depends on your weight, so most of us are just at mill power. When you see ones with extra tanks, or if you're really heavy, that's when you could do that.
So, it depends on the weight of the plane. If they are very loaded, will they put the afterburner on, okay? And now the reason, the moment we've all been waiting for. How many forces do you think were endured during the launch? Let's first see my face during the launch. I remind you that in the 102 we were turned around. And therefore, if you in a car when you accelerate you stick to the seat, here it would be the opposite. We would go forward, and for that we had a chest harness and a waist harness on. I leave you with the forces, GS. The catapult's acceleration is only along the plane's longitudinal axis as the plane accelerates from 0. Towards the takeoff speed, there is neither lateral nor vertical movement. The acceleration was roughly 1.8 Gs for 3 seconds, peaking at almost 3 Gs at the start. It was total chaos. Notice the glasses flying off the face. I had never experienced anything even remotely similar to how I felt at that moment. It was like all of a sudden, I'm remembering the feeling now. It was like all of a sudden, feeling like I wanted to stay there still, but something was pulling me towards infinity, backwards, really, with an impressive force. If we hadn't had the chest harness and the waist one, I probably would have smashed into the seat in front, but when I say smashed, I don't mean a hit. I don't think something serious really could have happened to me if I hadn't had the belt, but when I say something serious, really? With the force I felt, if I had hit the seat in front, I really think I would have been gone to the other neighborhood. Similarly, I also conducted a survey on how many Gs you thought would be endured at the moment of catapult launch, and the same thing happened here. After seeing surveys and comparing with actual G-force results, everyone said there were many more Gs than experienced. What I think is that all humans, myself included, tend to underestimate the power of G-forces. When they say we haven't had a 1G increase, it may seem insignificant, but a 1G increase is absolutely brutal. To illustrate, I flew from Madrid on an Airbus A320 and set the G-force meter during my trip there. Those who have flown on a plane know that during acceleration you're pressed against the seat. Well, there it didn't even reach 0.2 Gs, and the catapult was almost 2 Gs, constant for 3 seconds, 10 times more. Anyone who has flown in a 102 and has landed and taken off from an aircraft carrier, they will tell you that the moment of the catapult is much wilder than the moment of the cables. I want to stress the sensation of the catapult. It's been the most thrilling experience of my life. At that moment, you can't think about absolutely anything. When we landed, I was recording and laughing with the camera, but on the catapult, I was completely still, unable to move at all. And really, out of all the people who went, I was laughing, very excited and such. And at that moment, I was completely drained afterwards. If you look at my face, I am completely drained. Well, despite that, landing on an aircraft carrier is quite dangerous, the issue of catching the cable. Everyone who does it gets a diploma. Yes, from today, folks, I am officially a tail hooker, but it's really a snack compared to the takeoff, which in fact, I think is so wild. The feeling you get, because you feel the forces that are forward when we are really used to feeling them backwards and being pushed against the car seat. This concept has been researched, and I've even created videos discussing the varied perception of forces. Depending on which axis they are experienced on. So here comes my question, why then does the 102 have the seats backwards? If when you are going to experience, the wildest sensation is going to be on the catapult, and it is going to be forward. I don't have an answer, I've searched the internet, but I haven't found any answer that seems decent to me. So if anyone knows it, put it in the comments, and I'll pin it so everyone can see it. Thank you very much for watching this video. Subscribe because there are still 3 more videos about aircraft carriers, and I can tell you, they are absolutely crazy. See you in the next one.